Our next speaker is Sahana Balasubramanya, who will be talking about non-recognizing spaces for stable subgroups.
Thank you so much. It's my pleasure to be here, and my thanks to the organizers for inviting me to talk about some of my more recent work. So as the title says, I'm going to talk about non-recognizing spaces for stable subgroups. And I understand that there's probably a lot of terms in that title that people aren't familiar with. So let me start by defining some of them. And I'll start with the definition of a stable subgroup. So suppose you have a group G, which is finitely generated, and let's assume that we've picked a finite generating set for G. Let's call it A. Then in this situation, a finitely generated subgroup H of G with, let's say, we've picked a finite generating set B for H. Such a finitely generated subgroup is called stable if two conditions are satisfied. So the first is that if you consider the Cayley graph of H with respect to its finite generating set, then this QI embeds into G with respect to its finite generating set. So that's the first condition we need to be true. And then the second condition that we need to be true in order to qualify as being stable is that, and I'll write it this way, that H is Morse in G. By which I mean that in this space, the Cayley graph of G with respect to A, if you pick two vertices that lie in H and you have a lambda C quasi-geodesic between them, then quasi-geodesics of the same quality stay uniformly close to one another. And of course, the bound on the closeness is a Hausdorff bound, and it depends on the quality of those quasi-geodesics. So this is the same kind of Morse properties that hyperbolic spaces enjoy. And this notion was introduced by Durham and Taylor, and really it was introduced to serve as a generalization of the notion of quasi-convex subgroups of hyperbolic groups. And in this context, one can ask the following question. One can ask, does there exist a hyperbolic space X which is equipped with a G action such that every stable subgroup is QI embedded in X via the orbit map. In other words, this space X, does it recognize every stable subgroup of our group G? And if such a space exists, then we call X a recognizing space. Now, such a recognizing space is known to exist in many well-understood examples in geometric group theory. So I'm going to state a broad theorem which lists all these examples with the understanding that each one of the pieces that I talk about in that theorem are coming from a different source. So the theorem states that the following groups have recognizing spaces. And the first one in this example are those of mapping class groups. The fact that they have a recognizing space, it can be attributed to two different sources. One is a proof by Ursula Hammenstadt. The other is a proof by Kent and Leininger. And what they show is that it is actually the action on the associated curve complex which serves as a recognizing space. And of course, the fact that the curve complex is a hyperbolic space is due to Mazur and Minsky. The second example that's known in literature is that of right-angled Artin groups. So these are groups that are defined using graphs with commutativity relations. And their recognizing space is the extension graph. The fact that the extension graph is hyperbolic is due to work of Kim and Kuberta. The fact that the action on the extension graph is a recognizing space, that is due to work of Kuberta, Mangahas, and Taylor. And then the third list of examples that I'll talk about are those of hierarchically hyperbolic groups. And the recognizing space in this case, I will write this in quotations because I'm being slightly hand wavy here. This is the top level hierarchy space. By which I mean that for every HAG, there is a canonical decomposition into hyperbolic pieces of your group. And in this hierarchy, there is a top level domain or a top level space on which your group is acting. And that top level space is what provides the source for this recognizing space. The fact that the hierarchy spaces are hyperbolic is part of the definition of being a hierarchically hyperbolic space. The fact that this is a recognizing space is due to work of Carolyn Abbott, Berstock, and Durham. Now, the interesting thing about this list of examples is that all of the groups above are what we call acylindrically hyperbolic groups. So if you're unfamiliar with that term, sorry, but I'm not going to have enough time to define it. It's a very broad class of groups. It contains many interesting examples, not just the ones listed here, but it also contains all non-elementary free and hyperbolic and relatively hyperbolic groups. It contains fundamental groups of many manifolds out of Fn. So it's a very broad class of groups. And all of the examples that are in this list are acylindrically hyperbolic groups. And what's even more interested in is that the recognizing spaces here are the spaces which admit largest acylindrical actions for these groups. So what does that mean? Well, for an acylindrically hyperbolic group, one can first of all ask whether there exists a largest acylindrical action. So this has to be an action on a hyperbolic space, which is acylindrical, and it's called largest if every other co-bounded acylindrical action of your group, large-scale Lipschitz, embeds into your chosen action. So it's somehow retaining information that you could have read off any other acylindrical co-bounded action, which is why it's called the largest. And the fact that these actions listed here are the largest actions can be attributed to different sources. So the fact that the action of the mapping class group on the curve complex is the largest, that's due to work by me, Abbott, and Osin. The same thing goes for the action of the right angle Artin groups on the extension graph. We showed that that was the largest too. And for the hierarchically hyperbolic groups, this follows from work by Abbott, Berstock, and Durham. So one can ask the following question, keeping this list of examples in mind, that if an acylindrically hyperbolic, which I'll abbreviate to AH, so if an acylindrically hyperbolic group has a largest action, which is the first point of contention because the largest action may not always exist. And an example of such a group of an acylindrically hyperbolic group that doesn't have a largest action is, for instance, Dunwoody's group J. So in case your acylindrically hyperbolic group has a largest action, does the associated space recognize all the stable subgroups? So if there is a largest acylindrical action, do we know that every stable subgroup QA embeds via the orbit map into this particular hyperbolic space? And the answer, unfortunately, sadly, is no. And the counterexample is due to me, Marissa Chesser, Alice Kerr, Johanna Mangahas, and Marie Trin. This is a long list of authors. But what is the counterexample? The counterexample comes from the following setup. So Olshansky produced an example of a finitely generated group H such that every proper subgroup is infinite cyclic and Morse. For those of you who might be familiar with the term, this is actually a finitely generated lacunary hyperbolic group, which means it has one asymptotic cone, or at least one asymptotic cone, which is an R-tree. But it's not necessary that all of its asymptotic cones will be R-trees. In fact, this particular group H is going to have other asymptotic cones that are not R-trees. But notice that the group H itself is not acylindrically hyperbolic. And the reason H is not acylindrically hyperbolic is that it has no free subgroups of rank bigger than 2, which is one of the primary characteristics of an acylindrically hyperbolic group. They have lots and lots of free subgroups of higher rank, and the fact that every proper subgroup here is Z means that, of course, the group is not acylindrically hyperbolic. But there is a very easy way to construct an acylindrically hyperbolic group, and that is the construction of free products. So what we're going to do is take H and free product it with Z. And then, of course, it's easy to convince ourselves that because H is finitely generated and so is Z, G is also finitely generated. And G is going to be acylindrically hyperbolic because of a phenomenon that was introduced and studied by Dahmani, Girodel, and Osen. That is the notion of hyperbolically embedded subgroups. And their work tells us that when you take such free products, then H most certainly hyperbolically embeds into G. This is a proper non-degenerate hyperbolically embedded subgroup. And so we know that G is acylindrically hyperbolic as a result of that. This is a list of equivalent criteria to show that a group is acylindrically hyperbolic, to show that it has a non-trivial hyperbolically embedded subgroup. And in fact, in this case, because our Z is finitely generated, we can say a bit more. We can actually show that G is relatively hyperbolic, and our H is the peripheral subgroup. So the notion of being hyperbolically embedded is actually a true generalization of the notion of a peripheral subgroup. The difference in those two setups is that anytime we have a hyperbolically embedded subgroup H, we have an associated relative metric, and that relative generating set associated to H doesn't always have to be finite, but in case it is, then you're exactly in the situation when you have a relatively hyperbolic group and your hyperbolically embedded subgroup is in fact a peripheral. And something that Carolyn, Dennis, and I studied is that in the situation that G is hyperbolic relative to H, and the peripheral is not acylindrically hyperbolic, then our group G has a largest acylindrical action. And what is this largest acylindrical action? It is going to be the action on the relative Cayley graph. So this is the Cayley graph of the group G, where what do? We want to completely cone off our peripheral subgroup H, and all of its translates equivariantly. So my generating set is going to contain the entire subgroup H, and I'm going to throw in a stable letter T, where T is the generator of the Z factor in my group. And this is known as the relative Cayley graph. And what does this Cayley graph look like? Well, you have a complete copy of the Cayley graph of H with respect to itself. So this is a bounded set of diameter 1. And then you have the T edges branching out of this copy, which connect to cosets of this complete graph. And this picture iteratively keeps going on. So this space, it's not so hard to see, is actually quasi-isometric to a tree. And trees are hyperbolic. Hyperbolicity is a QI invariant. So our relative Cayley graph is a hyperbolic space for sure. And what can we see? We can see that this space is not a recognizing space for stable subgroups. And why is that? Well, the reason is if you pick your favorite element H and H, and you consider the infinite cyclic subgroup that it generates, this infinite cyclic subgroup is, by the properties of your group H, stable in H. It QI embeds into a finitely generated Cayley graph of H, and it is Morse because that's how the group H was constructed. And the fact that H is a peripheral means that H is malnormal in G. So it's sort of the opposite of normality, where your conjugates don't intersect with one another at all. And the fact that H is malnormal in G allows you to show that H is in fact stable in G as well. But this subgroup will never be QI embedded in this space, because over here we've completely destroyed the geometry of the subgroup H. It's completely coned off, so no subgroup can be QI embedded in this relative Cayley graph. So we have an acylindrically hyperbolic group with the largest action, and the largest action, sadly, does not serve as a recognizing space for stable subgroups. So something else that we're interested in, which follows from this counterexample, is which acylindrically hyperbolic groups with largest actions admit a recognizing space. So is it necessary that an acylindrically, the reason I put with largest actions in parentheses is it possible that you, first of all, have an acylindrically hyperbolic group that may or may not have a largest action? If it does have a largest action, can it admit a different recognizing space? And if it doesn't have a largest action, can there still be some other recognizing space? Are the two notions really even related to one another? And something that we'd like to look at in this context the inspiration for looking at this class of groups comes from the fact that right angle Artin groups are acylindrically hyperbolic and have a largest action. What we'd like to look at is graph products of groups, which are generalizations of rags. Instead of having infinite cyclic vertex groups, you can have arbitrary vertex groups. And that's something this collection of authors who produced this counterexample are trying to look at to see if we can produce a recognizing space in this more general setting. And I will stop here. Thank you very much.
All right, thank you, Sahana. Any questions from the audience? You can just unmute yourself. So you're looking at these graph products now. Are they are the things you're investigating from the graph products, are they also being built from these Tarski monsters in some way?
Being built from Tarski monsters. I'm not sure
what I meant was the Olshansky groups that you saw that you were using before.
Yes.
For the acylindrical example, are they also somehow related inside this graph product structure that you are looking at, or just anything, you know?
So I think we're going to need some conditions on the vertex groups that we look at when we look at these graph products of groups. Something that might save us, even if one of the vertex groups were these strange groups, is the fact that you have, a high degree of commutativity in a graph product of groups. So maybe that commutativity might still save you and leave you in a place where you don't have to worry about such groups turning up as vertex groups. But my impression is that we will need at least some conditions on these vertex groups if you want to somehow take the proof model for rags as inspiration and push everything forward to more general vertex groups. My impression is it's going to need certain conditions on vertex groups. And I think that in itself is interesting. Like, how much of the proof can you push forward with no assumptions? And when you come across a roadblock, what sort of assumptions do you actually need to impose? I mean, one could also more generally ask that if you knew all your vertex groups had recognizing spaces, does the graph product of groups immediately have a recognizing space then, right? That's something else one can wonder about.
Anyone else have questions? Okay, let's thank Sahana again.